Welcome to another CEO Wisdom podcast. We have John Bucknell with us today. John is CEO at Virtuous Technologies, Virtuous Solis Technologies, that is. We're going to talk about his serial entrepreneur background. He's also technical founder. Virtuous Solis Technologies is in space, it's solar power energy company. John has been founder at various companies, also worked at SpaceX for a year. Very interesting entrepreneur altogether. This podcast is brought to you by podfire.com. If you want to start to monetize your podcast, you can go to podfire.com. We help you get leads through podcasts, get sponsors, and get paid through YouTube AdSense. John, welcome to the podcast. Tell me a bit more about yourself and what you're up to nowadays.
Thank you, Charles. Happy to be here. So I'm an old guy. You can see my gray hair, but I've been in the technical field for a very long time. My dad worked in the Apollo program, so I've been around space for a very long time. But I took a detour in my career to work in mass manufacturing for a while. I actually worked on cars. I lived in Detroit for almost 15 years before joining SpaceX. Worked on a number of things. There are a lot of things you can learn about how to make things at scale for very low cost, working in the automotive realm. And I did that, and I produced about 8 production programs before getting headhunted out to run SpaceX's advanced propulsion division. I was in charge of the Raptor rocket engine and the vehicle it powered, which was called the Big Falcon rocket back then, but is now called Starship. I've been very eagerly awaiting the advent of low-cost commercial space launch. Certainly, the Falcon series have progressed that dramatically compared to what had been available before, but the promise of very low-cost access to space is what Starship is probably going to do. You might know last week Elon tweeted that they're going to go to Mars in 2 years, which is pretty crazy. I wish them all the luck. Certainly, the FAA is not letting their test series progress as fast as they might like, but I did spend a year with SpaceX developing those rocket engines and a number of other things that we can talk about later before I joined another startup called Divergent, which is just now launching product, but they're in the toolingless manufacturing realm where you take generative design, 3D metal additive manufacturing, and robotic assembly to replace what you might need to build anything that's large engineered structures. So you build vehicles for a number of customers, including General Atomics, and they have their own product line building vehicles for themselves. But I retired from there about 5 years ago to build this startup. Virtuous Technologies was incorporated in 2019, and we're building the first commercial space-based solar power plants. So that's the quick background. Happy to expand on any of that.
Right. So, how does one go from car chassis and powertrains worked at Chrysler, Daimler, Chrysler, GM? How do you take that and apply it to rockets?
It's a continuum. All the things that you might work on in combustion engines, which is where the realm I came from, apply to rockets. Rockets are just bigger. They're liquid fueled systems. So I had to spend quite a bit of time working on turbo machinery in my roles at General Motors, and I was deputy director of advanced propulsion at General Motors at the time that they came looking for me. But I'll tell you that the reason that I think SpaceX was looking for people who had background in those areas is that Tesla had just started hiring people from the automotive realm. They had not done anything like that from their inception through the early 2010 or so. And the rockets that SpaceX was building at the time looked very much like hand-built prototypes, or even artwork you might find from cottage type artists. And Elon had wanted his spacecraft, his rocket engines, to look more like mass manufactured devices, which can be approached very close to the cost of materials that they're provided with. So, given those two backgrounds and my the publications I'd done on a number of topics, they thought that I would be a good fit to help them run their advanced propulsion. So effectively, I was advanced propulsion at SpaceX. All of propulsion was only about 70 people in total, but we were working on 6 different rocket engines simultaneously. So um, those things were the reason when I came in for the interview. Elon's like, "Hey, I need these rocket engines to look better," and I said, "Well, look, you can't do that with things you've already engineered and tooled up unless you want to start over, basically." So he said, "Okay, fine, you're in charge of our newest rocket engine," and I was the first full-time person working on what now is the most powerful, most efficient rocket engine ever built.
Interesting. My question was more like the powertrain. It's like on four wheels, right? Spinning vs a rocket, which seems to be totally different. Still propulsion, right? It's like taking immense. Well, it's compressing some amount of force to create gigantic amount of force on the other end and propel an object against gravity, hoping to reach escape velocity and so forth. But was that drastically different, or was that part of your study? Was that something you were constantly studying and still familiar with, like launching rockets? Because that was your first launching rocket job, right?
I was first professional for sure, but as I said earlier, that I'd been around rockets for my entire life, so I was pretty familiar with. I would say, from an engineering perspective, the difference between combustion engines in cars and rocket engines on rockets is just a matter of scale. The rocket engine that I worked on was called the Merlin. It's the engine that powers the current Falcon 9 series. It's pump that pumps the fuel consumes somewhere around 5,000 horsepower, which is a lot compared to what a car has, but it's the same thing, just a lot more of it. So, yeah, the combustion processes and all the things you might do are very, very similar. So I would say that as a trained aerospace and systems engineer, you can apply your knowledge across the entire spectrum. So I have a background in nuclear power as well, and all those things are very, very similar fundamentally.
Did you have a successful launch at SpaceX? Because you stayed there for 1 year and then took a job back at Chrysler, which I guess the pay grade must have been like drastically higher. Did you get to launch something at SpaceX?
Yeah, I was actually there for the first Falcon 9 launch that got to the International Space Station. So that was a great thing. Certainly at
Wow.
the time, the Falcon was not a reusable rocket yet, but I was working during my tenure there on a throttle valve that helped the rocket land vertically so that they could become reusable. So that was progressing, and about 3 years later, they successfully landed that rocket on the ground. So I can watch from afar and see these systems get better over time, and now they've launched. I think the most reusable rocket they've done is about 24 times, which is 24 times better than the next best rocket on this planet.
Wow. And 1 year at SpaceX is the equivalent of 10 years at any normal job, right?
For sure, you're working a lot of hours. There's pressure to perform, but I'd say it's most startups are like that. You're spending a lot of effort, at least thought effort, on what you're doing, trying to find the shortest path from what you've been asked to do to getting it up and running. So yeah, startups are quite a bit more challenging, I'd argue.
Did you apply some of these lessons from SpaceX to Virtuous Solis?
There are things that SpaceX does very well, and I would model. Certainly, the biggest thing is that you're more of a flat organization, and everyone is ultimately responsible for what the components that they're responsible for. So, from designing them to manufacturing them to testing them to integrating them. So there's no hierarchy per se. You're not asking your boss to ask his boss to ask someone else above them what they want. You're ultimately responsible. And then there's similarly there's something we call systems engineering, which is trying to understand what the ultimate use case of your product is or your component is, and work on the requirements in that regard, such that you get the best possible result. So don't just take the requirements that are handed to you. Try to understand what the ultimate desire of the product, what it wants to be, and work towards that. So those types of things, I would argue, yes, those are things SpaceX should model. If you're watching SpaceX, you should model. The other big thing is building prototypes. Get hardware, build it fast, iterate. Don't spend a lot of time thinking about what you're going to do. Just do it.
Virtuous Solace is fascinating. Yeah, I'm gonna share my screen so that folks can understand what it does. But it is science fiction. It is like Star Trek type of stuff. Can you explain what you folks do and when you had that vision of a persistent global scalable energy from space?
Yeah. So as you know, I'm interested in space as a resource. Space-based solar power as a topic actually has been around for quite some time. It was first described in literature in 1921, so quite some time ago, and it was popularized by Isaac Asimov in a story called Reason in 1943, and that became part of the iRobot series. And engineering proposals started showing up in the late 60s, and work had been done on it through the 70s. And NASA actually spent quite a bit of effort from 1978 to 1980 trying to see whether it was feasible. They decided it was, and they asked for more than $1 trillion in today's money from the U.S. Congress in 1980. And Congress said, "Look, that just isn't economical because it would be 2006 before the first system would be operational, and that just doesn't make a lot of sense." And the reasons were that all the underlying technology had to be developed and paid for. So 40 years later, all the reasons why it didn't make sense back then make sense today. So the biggest enabler is low-cost commercial space launch, and we talked about that prior. The other big things is Moore's law and the development of semiconductor manufacture and the impact on automation that has since progressed quite a way. So if you want to build an energy technology, you want to build something that solves all the existing problems with energy today. And space-based solar power solves all of those because you take the solar panels and you put them in space where they're out of the shadow of the Earth, so there's no day or night, and there's no weather. And then the only other thing you have to solve is how to get the energy from orbit to the ground. And we've actually done that. We've developed a wireless power transfer technology that uses radio waves to move energy from orbit to the ground. And it is able to penetrate weather in the atmosphere with basically no loss because the water vapor and clouds and the components of the atmosphere are transparent at the longer wavelengths that we're using in radio frequencies. So that makes it a very useful technology because you can have energy anywhere you want it at any time. But then the bigger challenge is how to make it cost competitive with the other energy technologies on the ground. And we've leveraged our backgrounds in mass manufacture, these aerospace components, understanding orbits and placing things up there, and as well as the mass manufacture of electronics. So all those things combined together, we've made a hypermodular system that can build power plants of basically any size, as low as 100 megawatts, which is about the size of a small coal-fired power plant, up to gigawatt scale, which is what nuclear power plants are at. And you can build them in any size for any customer anywhere on the planet. That's really what Solis is all about, is building a power plant system that has none of the downsides of existing generation and all the potential upsides, and lowering energy costs for everyone, really.
Yeah, the cost of building this whole thing looks monumental, probably in the billions. So yeah, what's your plan to resell the energy to have a profitable company? Because the vision's amazing, right? And the value is there, but yeah, building that up seems to be very, very costly.
Well, I will tell you that these systems that we've designed have been engineered to cost from the get-go. So the early first-of-kind systems, before the mass manufacturing kicks in, are 3 to 5 times as expensive as an equivalent solar farm on the ground, on a dollar per kilowatt basis, which puts them in the hundreds of millions of dollars to build. And we're actually selling power plants. We're not selling the electricity that these systems generate, but those systems are less costly than an equivalent gas-fired or even nuclear power plant. But the interesting thing is that they generate a lot more energy for the amount of capital you're spending on to build these power plants. And that's because they can operate year-round, 24 hours a day. So the cost is spread over a lot more energy. So its unit cost is only maybe 30 to 40% more expensive than the electricity generated by a conventional solar farm. But that's for a very small system. And economies of scale are a thing. You can build things bigger, and they work better. So at nuclear power plant size, which is 1,500 megawatts or 1.5 gigawatts, our systems are only 1.5 to 2 times as expensive as a solar farm on a per kilowatt basis. But the energy costs are half. So at the end of the day, we're selling to project financed customers, people who would be building power plants anyway, and giving them a deal where they're able to have less costly energy for not very much more capital. So less than a nuclear power plant and a bit more than a solar power plant. But at the end of the day, the energy generated is very inexpensive.
So, from a non-technical perspective, I'm gonna try to tell you what I understood of the company, and you tell me why I'm wrong. So, you build your own spaceships, right? Is that like a good start?
Our satellites aren't technically spaceships. They don't fly on their own. They don't have any.
But to deliver these satellites, the rocket, like, do you build that, or
No,
would you
no,
rent
no.
that from SpaceX, for example?
Yeah. We actually, because these are project financed um, purchases from the end users, the logistics, the delivery of the components to their place is something they're going to contract. So we're
Okay.
launch agnostic, but we will qualify the launchers, for our payloads. So obviously we're targeting SpaceX because their costs are lowest, but any other provider that wants to qualify their launcher, we will put our payloads on them and offer our customers the opportunity to competitively bid the launch services to anyone that's capable of doing so.
Okay, so you built the satellites and the panels technology, right?
Correct.
And the satellite carry the panels, so that's in one payload, right?
Yep, the satellites have the solar cells and the power electronics and the radio transmitters all integrated. And then there's a receiver on the ground that also has the ability to turn the radio waves back on electricity. And we manufacture both of those things.
Okay, so you'd launch the satellite, let's say one or two. Would you like also deliver the full solar panel? How much panels are there? Initially, 100.
So each satellite is about 500 watts to the ground. So if someone wants to build a power plant of 100 megawatts, that's 100,000 kilowatts. That's about 200,000 individual satellites all linked together in a large array. So
Whoa.
at 200,000 elements, and they're not big. This model I carry around is about the right size. So it's fairly thin, and you can stack them like your IKEA furniture might be. With the payload bays on the SpaceX Starship, we can put about 25,000 satellites on one launch. So it's 8 launches to put the entire system up.
Okay, very interesting. Are these? What's your plan against space debris?
Space debris, obviously, we don't intend to generate any. The orbit that we're in is relatively high compared to the debris that's low in low Earth orbit. So these systems are basically intelligent devices. They're like a cell phone or a laptop. So they do have smarts in them, and they can keep track of where they are, their status, their health, and all those interesting factors. But we'll put these together in arrays, and they'll be mechanically linked, and there'll be robots up there maintaining it. But our goal is to be up there basically forever. These systems are solid state electronics. We're designing for 40 years or more life, and they probably will last to 80 years. So we keep them up there and we maintain it just like any other solar farm. So if something fails or goes offline, we'll have spares and we'll remove and replace an entire satellite component at a time. And we can bring it all back down if we wanted to, but we don't think there's as much value for that. Certainly there are salvage companies out there that would like to buy these components as they go offline. They're mostly made from glass, and so they can be reused and recycled for radiation protection for satellites or other devices. So at the end of the day, not only will we not make space debris, but the end of life usage will be something that will be beneficial to other use cases.
And nothing will hit them with 200,000 of these things.
Yeah. The debris in low Earth orbit is only up to about 2,000 kilometers altitude, and it's not very dense. Space is pretty empty. We talk about there being one times 10 to the minus eighth debris per cubic kilometer in orbit. So it's pretty few number of device things, but we're at 35,000 kilometers altitude. So quite a bit higher than what we would call the space debris. But even so, our systems are massively redundant. So these 200,000 elements are all operate autonomously. They just are mechanically linked. So even if one or two or even up to 10% of them get hit and they fail, the system will still operate and will not generate additional debris because they're fully integrated. So we're fairly robust to that, and again, because they're large enough and smart enough, they won't create additional debris by themselves.
Right. Okay. And then you have this whole chunk of glass, many glass panels together, generating energy from the sun. The satellite has a smart code into it to come back and fetch these glass panels one at a time, right? Or
If you want to bring it back down to the ground, you can bring them back down the same way you put them up. You put them in racks of a few hundred, and then you put them on a rocket. You can do the reverse and bring them all back down. But we would argue that the end of life, they're probably going to be used for something else somewhere in space, as opposed to bringing them back down to the ground.
yeah, I meant for the energy generating part because it seems to grab the panel so that it can reflect microwave back to Earth and generate energy, right?
Yeah, so we actually do the energy collection in orbit on the satellites. The satellites turn sunlight and electricity. Then we turn the electricity into radio waves and we beam it to the ground, just like a radio transmitter. Our technology has a lot of similarities to radar. So the packets of energy come down as photons. It's just a longer wavelength. We're about 3 centimeters wavelength as compared to visible light, which is 350 to 1200 nanometers. So very, very much longer wavelength that allows us to pass through weather and clouds. And then the receivers on the ground just are tuned for that much higher wavelength system and converts it back to electricity. So the wireless power link is what we call it, and it's just a form of radio waves that we have today that we use for communication.
Okay, and that wouldn't disrupt planes, that wouldn't disrupt wildlife, the environment, anything?
No, we very carefully design our system so it was not harmful at all. The biggest thing about any source of photons is you want to care about the intensity. The intensity of our system is about a quarter of sunlight at maximum, just because of the chain of efficiencies from the sunlight in orbit and having to go through solar cells and down convert it. So the FCC in the U.S. regulates the intensity of radio sources. So in order to commercially deploy, you have to get a radio broadcast license. The broadcast license says you won't interfere with anyone and you won't hurt anyone. And that's requirements for us to build these power plants. So yes, very specifically designed to not be able to harm anyone or anything as a condition of getting commercial licenses necessary to operate these power plants.
Fascinating. We'll be respectful of time here. I have so many other questions. Maybe we can do a round two in a couple months from now. But where can people find out more about you, John?
So our website is vertisolis.space. Vertisolis is Latin for power of the sun. So really our website's name is Space Solar Power. And you can, there's a contact form there if you want to reach out to us directly, and we'd be happy to answer any questions.
That was John Buck.